This is Lab 5 for Faraday's Law. The purpose of this experiment is to observe a current which produces a magnetic field and thus produces a force on the source of magnetic field. And this is going to be completed using a small bar magnet as the source of the external field and the aluminum foil tube as the driver of induced current. In this lab, we'll also see the physics concepts of Faraday's law highlighted in yellow, the Biot-Savart law next to the Faraday's law, and then Newton's second and third laws. The setup for this experiment, as mentioned before, includes the use of a small bar magnet and an aluminum foil tube, and a smartphone to record and observe the time in which the magnet enters and exits the tube. The measurements for the length of the tube, mass of the magnet, width of the foil, the inner radius, and the outer radius are shown on the right. There are two videos from my experiment in which you can see the comparison between the free fall on the left and the falling through the tube on the right. And just initially, the observation was that free fall was much quicker than when the magnet was dropped through the foil. Here you can see some of the first parts of the code, including the setup for the geometry of the tube, as well as creating the properties of the magnet and visualizing the magnet, and then also including the code similar to that in Lab 3, which will create a function which calculates the magnetic field of the bar magnet. Here you can see a continuation of the code, which includes the defining of the function to calculate the flux through each ring due to the falling magnet, as well as the magnetic force and the net force, and the magnet velocity and position, and a graph of the velocity and time of the magnet as it falls, and finally, the total time in which the magnet was in the tube. This slide shows the output and visualization of the code shown on previous slides. You can see the representation of the tube as well as the bar magnet within the tube. And then on the right, this is the graph of the velocity and the time during its fall. You can see the final calculation of the time in which the magnet was in the tube as 2.28 seconds calculated by the code, and you can see that as well visually above when the velocity was at a constant rate. Results of both the experimental and model calculations are shown below. You can see that the average experimentally calculated time is 1.7 seconds. In the table to the right, you can see that each trial had similar times, and the average of that is 1.7 seconds, as mentioned before. The model calculated time is 2.28 seconds, and you can see the calculations due to the code on the previous few slides. And this discrepancy could be due to human error. Basically, if I wasn't dropping the bar magnet straight into the tube, or if I incorrectly timed, since it was only a simple iPhone video, there could have been a more precise way to measure the time. And also the model doesn't really account for air resistance, so there could have been some error there. To conclude, I'll be answering the what if questions given in the lab. So if the resistivity of the conductor were reduced as close as possible to zero, the dynamics of the falling magnet would change in that it would fall slower due to the increase in induced current. Also, if the tube had holes or slots cut into it, this would affect the ring currents in that it would create less rings in the tube and thus cause less of a force from the magnetic field, and the magnet would then fall even slower. Thank you.